All right, so let us begin by taking a look at and beating up on our three-layer network model. So now with this model, it was said to be best suited when we had more north-south communication in the data center as opposed to east-west. So north-south is where we're entering and exiting the data center, and east-west is where we have our server-to-server communication. Now the problem with this model has to do with the amount of real estate that we have for layer 2. We can see that it extends all the way up from the access layer and goes up to the distribution layer. This is going to introduce a few things. We're going to see that it's going to be, kind of difficult to manage this because of this large area of layer 2. It's going to be very resource intensive. And we're also going to see that there's going to be some risk factors associated with this. So all of this is going to stem from just how we go about learning within our networks. So first off, if we start down here, so on our end stations, right, we have the TCP/IP protocol suite. And what's in that suite is good old ARP, right? So ARP is how we go about doing our network discovery. Now, when we're going to do this discovery, we can see that our network edge resides at the distribution layer. So we're going to be broadcasting, and this is going to create a lot of chatter in this region right here. So one thing that we've done to kind of a hold on this is we had to manage it. And the way we go about managing that to reduce the amount of traffic that goes across the trunk links is we do this either allowing or denying VLANs to go across it, or we prune them, right? So that's one thing that we needed to do here because of the resource intensiveness of the way that we learn. The other thing that has to do with learning, and we're going to see that this is more of a big pain, right, is spanning tree. So with any good architecture, we're going to want redundancy, right? And with spanning tree, this is going to be used to kind of mitigate broadcast storms, right? So if we kind of go through this, right? So with our switches, the way that they learn is they're going to broadcast out all active ports except the one they came in on. And if we form a loop, this is going to introduce a broadcast storm. So now what we're going to do to manage spanning tree, first thing we're going to want to define is where the root is. So everything's going to flow towards the root. So we're going to want the root to be in these upper layers right here. For example, in this illustration, it's going to be at the distribution layer. Next thing we're going to manage is where we're blocking our ports. So we're going to want to manage that as well. And then there's going to be some risk factors associated with spanning tree. Because if there's any changes to what we define here, for example, who the root is, so if someone plugs in a device and we don't have the safeguards, the configs in there to prevent that, then someone could divert traffic, right? The other thing someone could do if we don't have the proper configuration or safeguards in place is they could introduce a device that can form a loop and take down our network. And those are always, in the back of our mind, those risk factors. However, we also can see that spanning tree is kind of like a resource hog, right? A common, implementation of spanning tree that we use in an environment like this is rapid spanning tree. So per VLAN spanning tree, right? So for every VLAN we have a unique instance of spanning tree. The more spanning tree instances and the more active ports, the greater the CPU utilization. So now if we can kind of limit all of this stuff by reducing the amount of real estate that we have for layer 2, as we're going to see with spine leaf, this is going to kind of, take away all of those shortfallings of such a large area of layer 2. Okay, so now the last thing I'd like to discuss here in terms of the limitations of this design has to do with oversubscribing links. So link oversubscription within your, within your architecture, this is something that we have to manage, right? However, we're going to see that there's a major limitation to this, once again, because of this large area of layer 2. So let's kind of walk through this a bit. So if we take a small data center as an example, we'll typically find all of this networking equipment right here confined to one row. And we'll have many, many rows of servers. Some common connections that we might find coming from those servers and added to the network can be seen right here. So we have our front end 1, front end 2. We have our ILO, which is our management, and we have our backup connections. The way that we're adding these connections to the network is we're connecting them via an overhead patch panel. And then those connections are run across the data center to that network row and then to those switches. Now, as you can imagine, if we're doing this for every single server rack, we have this, possible bottleneck forming, right? And the way that this architecture and a lot of architectures for that matter, the way that they kind of handle this is they throw port channels at everything. Now, the problem that we're going to have is not only the limitations because of that large area of layer 2, but also the port channel itself. So with your port channels, you can logically group 16 connections together. You can have 8 of them active, 8 of them standby. And if we go ahead and oversubscribe this link over here, we simply just can't add another one because we'd have spanning tree to deal with. Once again, spanning tree looks to block a port anytime we form a loop. So we have kind of like we have the limitations of the port channel, but then we also have the limitations due to the design.